Good evening. On this channel, I guide you to stars and other interesting objects nearby in our galaxy. I'm an AI voice, just so you know, but I hope you like me anyway. Tonight, we'll turn our gaze to Sirius, a truly remarkable star, only 8.6 light-years from the solar system. Sirius is the second closest star visible to the naked eye, after Alpha Centauri, and holds the title of the brightest star of all thousands of stars we can see in the night sky. With an apparent magnitude of -1.46, Sirius shines nearly twice as brightly as Canopus, the second brightest star visible to the naked eye from Earth. The name Sirius originates from the Greek word Sirios, meaning glowing or scorching. As the brightest star and visible from essentially all populated areas of our globe, Sirius has a long and deep observational history and significance for many, if not all, ancient cultures of humanity. Many of these ancient cultures, Greek, Persian, Chinese, and American to name a few, have related the star to myths about dogs, suggesting these myths could have a common, very old origin. In any case, Sirius is often called the dog star, being the most significant star of Canis Major, the Great Dog constellation. Sirius is part of a binary star system, consisting of a primary main sequence star of spectral type A0 or A1, known as Sirius A, and a faint white dwarf companion of spectral type Da2, termed Sirius B. Sirius B is the closest white dwarf of all to the Earth. The distance between these two stars varies significantly, ranging from 8.2 to 31.5 astronomical units, AU, and they orbit each other every 50 years. From here on, I will refer to Sirius as one star, unless I specifically mention either Sirius A or Sirius B. Sirius is visible from nearly all inhabited parts of the Earth, with the exception of extreme northern latitudes. Its visibility depends on the time of year and the observer's location, as Sirius has a declination of about -17 degrees. At times, Sirius shines brighter than both Mars and Mercury, depending on their respective position in their orbits. At its brightest, during opposition, Mars can reach an apparent magnitude of 2.9, making it brighter than Sirius. But when Mars is farther from Earth, its brightness diminishes, and it can become dimmer, with a magnitude of around +1.8 at its faintest, making Sirius the brighter object in comparison. Mercury, being closer to the Sun, can be difficult to see and also fluctuates in brightness. At its brightest, Mercury reaches an apparent magnitude of -2.0, which is comparable to Sirius but slightly dimmer. At other times, Mercury can become much fainter, with a magnitude of +5.7, making it far less bright than Sirius. In the northern hemisphere, Sirius becomes visible from late November through April, with the best viewing period during the winter months of December to February. During this time, Sirius rises in the early evening and remains visible for much of the night. In regions like the United States, Europe, and Japan, it reaches its highest point in the sky around midnight in January, though it stays relatively low in the southern sky. Further north, such as in Scandinavia and Russia, Sirius can only be seen from late December to early April, and it remains low on the horizon, reaching a maximum altitude of about 13 degrees. Beyond 73 degrees N latitude, such as in parts of northern Canada, Alaska, and Norway, Sirius never rises above the horizon and is not visible. In equatorial regions, Sirius is visible for a large part of the year, from late October through mid-May. In cities like Nairobi, Quito, and Singapore, Sirius appears nearly overhead in the sky during the winter months, making it an especially bright and striking feature. It is best seen from November to March, with culmination, its highest point in the sky, occurring around midnight in January. In the southern hemisphere, Sirius dominates the summer night sky and is visible from early August to mid-May. From locations like Sydney, Buenos Aires, and Cape Town, Sirius reaches a high altitude of nearly 70 degrees, making it a major feature of the summer months, particularly between December and February, when it is visible all night. In tropical regions such as Cairo, Mexico City, and Honolulu, Sirius is visible from late October through mid-May. Its brilliance is especially noticeable during the clear winter nights of December through February, and its culmination occurs around midnight in January. Its heliacal rising, which takes place in mid-July, historically marked the flooding of the Nile in ancient Egypt, symbolizing the renewal of the land. The heliacal rising of a star or planet occurs annually when it first becomes visible above the eastern horizon at dawn, just before sunrise. This event marks the return of the star after being obscured by the sun's glare, and during this brief period, it is often referred to as a morning star, shining in the early morning sky before the sun rises. For those in the far southern regions, such as southern Chile, Argentina, and Antarctica, Sirius is visible from July through early May, with the best viewing period occurring during the austral summer months of December and January. Here, Sirius rises high in the sky and remains visible for most of the night. Sirius can be seen in daylight with the naked eye under ideal conditions. For this, the sky needs to be exceptionally clear. The observer should be at a high altitude, and the sun should be low on the horizon while Sirius is passing overhead. These optimal viewing conditions are easier to achieve in the southern hemisphere due to Sirius's southerly declination. Sirius is the most prominent part of the Great Dog constellation, or Canis Major, more specifically one of Orion's hunting dogs. Sometimes in depictions it forms the nose, but it can also be the point which ties the head and body together, like a jewel in the collar around the neck. The constellation Canis Major is home to several other notable stars, such as Adhara, Wezn, and Mirzam, which are also quite bright but overshadowed by Sirius's brilliance. Adhara, for example, is a binary star system and the second brightest star in Canis Major, while Wezn is a supergiant that appears fainter due to its great distance from Earth. Sirius is part of a larger and famous asterism known as the Winter Triangle, which also includes Betelgeuse in the constellation Orion and Procyon in the constellation Canis Minor. These three stars form a large, easily recognizable triangle in the winter sky of the northern hemisphere. The proximity of Sirius to Orion is particularly striking. Orion, with its well-known belt of three stars, Alnitak, Alnilam, and Mintaka, is one of the most famous constellations and can serve as a guide to locate Sirius. Following the line created by Orion's belt stars downward to the southeast leads directly to Sirius. Sirius and Canis Major lie close to the plane of the Milky Way, so when observing this region of the sky, you are also looking at part of our galaxy's rich star field, and more specifically, you are looking towards some of the spiral arms of the Milky Way. On a dark, clear night, away from light pollution, the Milky Way's band of stars, gas, and dust clouds forms a striking backdrop. The concentration of stars in this area makes it a beautiful region to scan with binoculars or a telescope. Sirius is, as mentioned, one of the most well-known stars in the night sky, and its name has evolved over millennia, shaped by the cultures and languages that have observed and revered it. The Romans continued the Greek tradition of the dog star, naming the star Canicula, or little dog, during the height of summer. This name gave rise to the term dog days of summer, referring to the period of extreme heat during the star's heliacal rising in July and August. In ancient Egypt, Sirius was known as Sopdet or Sothis, and it was personified as a goddess. She was often depicted as a woman with a star on her head, representing the life-giving power of Sirius. In Arabic, Sirius is known as Al-Shira, Al-Shira'a, derived from the word for leader or chief. This name is referenced in Surah An-Najm, the star, of the Quran, where the star is described as Al-Shira Limnik, Al-Shira al-Yamaniya, meaning the leader of the Yemeni. In Islamic tradition, Sirius was important in the Bedouin astronomical system, where stars were used for navigation in the desert. The name Al-Shira also appears in medieval European texts, where it was Latinized as Asher by early astronomers like Johann Bayer. In Sanskrit, Sirius is called Murgavyada, which means the deer hunter. The star is also associated with the god Rudra, an early form of Shiva in Hindu mythology. Sirius's role as a celestial hunter aligns with its placement near Orion, another constellation associated with a hunter figure. Sirius held significant importance in Polynesian cultures, where it was used for navigation across vast expanses of the Pacific Ocean. The Maori of New Zealand referred to the star as Takurua, which was both the name of the star and the season of winter, marked by Sirius's prominence in the night sky. In Hawaii, it was known as Kaulua, meaning Queen of Heaven. Other Polynesian names for Sirius include Tauua in the Marquesas Islands and Rehua in New Zealand, both of which reflected its role as a marker of time and seasons. In Old Norse mythology, Sirius was known as Lokabrenna, which translates to Loki's torch. This name possibly associates the star with the Norse god Loki, known for his mischievous and unpredictable nature. The connection to Loki, a trickster god who often caused trouble among the gods, adds an element of unpredictability and perhaps reflects the ancient Norse perception of celestial bodies as having personalities or divine significance. Indeed, Sirius is somewhat of a trickster star of various twinkling colors to the eye. In medieval Europe, Sirius was also referred to as Alhambor, a name commonly used in conjunction with astrolabes, the ancient astronomical instruments used for navigation and star tracking. This name appears in Geoffrey Chaucer's treatise on the astrolabe, 1391, one of the earliest known instructional texts on the use of this instrument in England. In the treatise, Sirius is depicted as part of the constellation of a hound, aligning with its traditional role as the brightest star in Canis Major. The name Alhambor is thought to have derived from an Arabic term, reflecting the influence of Arabic astronomy on medieval European thought. In modern astronomy, Sirius is officially designated a Canis Majoris, indicating that it is the brightest star in the constellation Canis Major. The name follows the Bayer designation system, where the Greek letter A is assigned to the brightest star in a constellation. Sirius is often abbreviated as a CMA in astronomical catalogs. Once it was visually confirmed that Sirius was a binary system, the two stars were called Sirius A and Sirius B, according to the standard astronomical convention, where the brighter star in a binary system is labeled A, and the fainter companion is labeled B. Sirius B is sometimes nicknamed the Pup, a playful reference to the fact that Sirius is often called the dog star. Sirius has been the subject of astronomical observation for centuries. As mentioned, the ancient Egyptians and Greeks meticulously recorded the star's heliacal rising, which was of great practical importance. Its apparent position relative to the ecliptic made its annual heliacal rising almost perfectly regular, with a period of about 365.25 days, making it a reliable marker for the solar year. The star's proper motion was first noted by the English astronomer Edmund Halley in 1718, who observed that Sirius had moved significantly compared to the background stars since ancient times. This discovery challenged the then prevailing belief that the stars were fixed in the sky. In 1868, Sir William Huggins made another significant contribution by measuring the radial velocity of Sirius, marking the first time this technique was applied to a star. Huggins observed a redshift in Sirius's spectrum and concluded that the star was receding from the solar system. Although his initial estimate of the velocity was incorrect, it laid the groundwork for the study of stellar motion. Around the same time, Sirius B was discovered by Western astronomers. In 1844, the German astronomer Friedrich Wilhelm Bessel noticed something unusual. The motion of Sirius wasn't completely smooth. Instead, it seemed to wobble, suggesting that Sirius might be gravitationally influenced by an unseen companion. Bessel theorized that Sirius was part of a binary star system, with the visible star being orbited by an invisible companion. This hypothesis was bold, as no telescope at the time had yet detected such a companion. Bessel's prediction was confirmed almost 2 decades later. On January 31, 1862, Alvin Graham Clark, an American telescope maker and astronomer, became the first person to observe the faint companion to Sirius. Clark was testing a new 18.5-inch refracting telescope at the Dearborn Observatory in Illinois, one of the largest telescopes in the world at the time. While conducting these tests, he noticed a faint star near Sirius, which turned out to be the companion star that had been eluding astronomers for years. This faint star would later be named Sirius B. After Clark's observation, astronomers quickly began confirming the existence of Sirius B using smaller telescopes. The star was much fainter than Sirius A, around 10,000 times less luminous, which explained why it had gone unnoticed for so long. Although it was faint, Sirius B had a mass nearly equal to that of the Sun, suggesting that it was an extraordinary type of star. Over the following years, astronomers studied the orbital motion of Sirius A and B, confirming that the two stars orbit each other every 50.1 years. The discovery of Sirius B was a major validation of Bessel's hypothesis and demonstrated that many stars in the sky might be part of binary or even multiple star systems. Sirius B was not only remarkable for being the companion to the brightest star in the night sky, but also because of what it represented. In 1915, American astronomer Walter Sidney Adams studied the spectrum of Sirius B and found that, despite its faintness, it had a surface temperature significantly higher than Sirius A, about 25,000 K. However, the star was also incredibly small, with a radius similar to that of Earth. This led to the conclusion that Sirius B was a white dwarf, a type of star that had exhausted its nuclear fuel and collapsed into an incredibly dense state. This was a groundbreaking discovery. Sirius B became the second ever known white dwarf, after 40 Eridani b. One of the most intriguing aspects of Sirius is the historical controversy regarding its color. Ancient texts from various cultures, including those of Claudius Ptolemy and Seneca, describe Sirius as a reddish star, which contrasts sharply with its current blue-white appearance. This discrepancy has sparked considerable debate and speculation among astronomers and historians. Several theories have been proposed to explain this apparent change in color. Intrinsic theories suggest that Sirius B, now a white dwarf, may have been a red giant star as recently as 2,000 years ago. This theory is generally dismissed due to the timescales involved in stellar evolution, which make such a rapid change highly unlikely. Extrinsic theories propose that the color change could be due to external factors, such as the interstellar medium or the Earth's atmosphere. One hypothesis is that a transient dust cloud passed between Sirius and Earth, causing the star to appear redder temporarily. However, while a temporary dust cloud between Earth and the Sirius system could cause some reddening, it would not be enough to make Sirius appear as red as stars like Betelgeuse or Arcturus. Such reddening would also significantly dim Sirius, contrary to historical records, which describe Sirius as very bright. The level of dimming necessary would make Sirius appear faint to the point of being invisible to the naked eye without a telescope, which doesn't match the historical descriptions. Another explanation could be atmospheric conditions that affected the perception of Sirius when it was observed near the horizon, where stars often appear redder due to atmospheric scattering. Cultural factors may help explain why some ancient observers reported Sirius as red, particularly when it was seen low on the horizon, where it would naturally appear redder due to atmospheric effects. In several Mediterranean cultures, the heliacal rising and setting of Sirius were considered astrologically significant, making the star's appearance, whether bright and clear or dimmed, of great interest and the subject of systematic observation. As a result, Sirius was often observed and recorded while it was near the horizon, where it would appear redder. In contrast, other cultures like the Chinese, who did not attach the same astrological importance to Sirius's horizon position, consistently recorded it as white. Despite the numerous theories, there is no definitive explanation for the ancient descriptions of Sirius as a red star. The most plausible explanations involve a combination of atmospheric effects and cultural factors that may have led ancient observers to report Sirius as red under specific conditions. The study of infrared radiation from Sirius has provided important insights into both Sirius A and Sirius B, as well as the surrounding environment in the Sirius star system. Sirius A emits more infrared radiation than would be expected solely based on its temperature and stellar properties. This excess infrared radiation has been observed through space-based infrared telescopes, such as the Infrared Astronomical Satellite, IRAS. The additional infrared emission has led to the hypothesis that there might be dust present in the Sirius system. The infrared data suggests that there may be a disk of material or residual dust surrounding Sirius A, potentially left over from its formation or from interactions between the two stars. Sirius B, as a white dwarf, also emits infrared radiation, though it is faint compared to Sirius A. Despite this faintness, infrared observations are crucial for understanding the temperature and cooling rate of Sirius B. As white dwarfs cool over billions of years, they gradually emit more energy in the infrared part of the spectrum. Studying this radiation helps astronomers estimate the age and thermal history of Sirius B, giving insights into how long it has been in its white dwarf phase, around 120 million years. The intense gravitational field of Sirius B also affects how radiation, including infrared, escapes from its surface, and studying its infrared profile can provide information about the star's surface composition and structure. Infrared radiation from both Sirius A and Sirius B is also used to probe the interstellar medium surrounding the system. Because Sirius is relatively close to Earth, 8.6 light-years away, astronomers use infrared telescopes to look for any faint background objects or structures in the vicinity, such as faint stars or substellar companions. However, infrared observations so far have not shown any presence of large planets or companion stars in close proximity to Sirius A and B. Sirius B, being a dense white dwarf, is a significant source of X-ray radiation. Sirius B no longer produces energy through nuclear fusion. Instead, it radiates energy from the residual heat stored during its earlier evolutionary phases. The extremely hot, compact nature of Sirius B results in the emission of high-energy radiation, including X-rays. Although Sirius A is a much brighter and more massive star than Sirius B in visible light, it emits only weak X-rays. As a main sequence star of spectral type A, Sirius A does not have the conditions to generate strong X-ray radiation. The X-rays detected from Sirius A are likely produced in the outer layers of the star's atmosphere, or possibly due to interactions with Sirius B. Now let us look closer at the actual binary star system of Sirius. Sirius A, the primary component of the Sirius system, is a main sequence star with a spectral type of AO or A1. It has a mass of about 2.063 times that of the Sun, M, and is approximately 25 times more luminous. The star has an absolute visual magnitude of plus 0.43 and a radius about 1.71 times that of the Sun. This high luminosity is a direct result of its mass and surface temperature, which place it well within the main sequence on the Hertzsprung-Russell diagram. The effective surface temperature of Sirius A is around 9,940 K, giving it a white or bluish-white appearance. For reference, the temperature of the Sun is about 5,700 K. Sirius A has a relatively slow rotational velocity compared to other stars of similar size and type. Its projected rotational velocity is about 16 kilometers per s, which is considered quite moderate for an A-type main sequence star. This is in contrast to some other stars of similar spectral type, such as Vega, which rotates much faster at around 274 kilometers per s. The slower rotation of Sirius A means that it does not experience significant flattening at its poles, which is common in rapidly rotating stars. The moderate rotation rate also affects the star's magnetic field and internal structure, leading to more stable conditions in its outer layers. Sirius A has a weak magnetic field, especially when compared to rapidly rotating stars. The presence of a magnetic field on a star like Sirius A is even somewhat surprising, given its relatively slow rotation. This could be due to subtle convective processes in the outer layers of the star or remnants of magnetic activity from earlier in its life. Sirius A is relatively young in terms of stellar evolution. Its age is estimated to be between 200 and 300 million years. The Sirius system as a whole is believed to have formed around 230 million years ago, and during this time, Sirius A has remained on the main sequence, where it burns hydrogen in its core. Over time, Sirius A will exhaust the hydrogen in its core and begin to evolve into a red giant, eventually shedding its outer layers and collapsing into a white dwarf, much like its companion, Sirius B, which has already completed this evolutionary process. Sirius A represents a typical, though relatively massive, main sequence star. It is classified as an A1V star, which means it is a main sequence star of spectral type A1. The A in the classification refers to its surface temperature of approximately 9,940 K, giving it a bright blue-white appearance. Stars of spectral type A are relatively hot and luminous compared to other main sequence stars. The V denotes that Sirius A is still in the main sequence phase of its evolution, where it is actively fusing hydrogen into helium in its core. Sirius B is a white dwarf, one of the most massive known, with a mass of approximately 1.02 m. Despite its mass, Sirius B is incredibly compact, with a radius comparable to that of Earth, leading to an extremely high density. The surface gravity of Sirius B is approximately 400,000 times stronger than that of Earth. To put this into perspective, if you were to stand on the surface of Sirius B, which isn't possible due to its searing temperatures and extreme conditions, a person weighing 70 kg, 154 lbs on Earth, would weigh 28 million kg, about 62 million lbs, on Sirius B. According to observations made using the Hubble Space Telescope in 2005, astronomers measured Sirius B to have a diameter of approximately 12,000 kilometers, 7,500 miles, very close to the diameter of Earth, which is about 12,742 kilometers, 7,918 miles. Is it not peculiar how often in astronomy there seem to be coincidences, like in this case, Sirius B having roughly the mass of the Sun and the volume of Earth? Or is this just physics and the human nature wanting to relate? The surface temperature of Sirius B is, however, very hot, around 25,200 K, thus significantly higher than that of Sirius A. Its faintness, despite the heat, is due to its small size and lack of ongoing nuclear fusion. Sirius B's rotational speed is difficult to measure directly, but as a white dwarf, it is expected to have a relatively slow rotation rate compared to its previous stages of stellar evolution. White dwarfs tend to rotate much more slowly than main sequence stars because of their compactness and the conservation of angular momentum during the collapse into their current state. However, the small size of white dwarfs still makes them rotate all the way in a relatively short amount of time. Based on studies of other white dwarfs, Sirius B's rotation could be in the range of a few minutes to several hours, but the exact rotation rate of Sirius B is not well known. Sirius B exhibits a weak magnetic field, a common feature among white dwarfs, though the strength of magnetic fields in white dwarfs can vary significantly. The origin of magnetic fields in white dwarfs is still a subject of research, but it is believed to be related to the evolution of the star during its earlier phases, particularly during the red giant stage and the star's subsequent collapse into a white dwarf. Sirius B is estimated to be around 120 million years old as a white dwarf, though the entire Sirius system is roughly 200 to 300 million years old. Sirius B was, as mentioned, originally the more massive star in the system, which caused it to evolve more quickly than its companion. The original star had an estimated mass of around 5 times that of the Sun and was likely a B-type star, specifically B5V, when it was on the main sequence. During this phase, it may have been 600 to 1/1200 times more luminous than the Sun. As it evolved into a red giant, Sirius B likely shed its outer layers, possibly enriching the metallicity of its companion, Sirius A, which could explain the unusually high metallicity observed in Sirius A today. More on this in a bit. Despite its relatively young age as a white dwarf, Sirius B will continue to cool over the next billions of years. Since white dwarfs no longer undergo nuclear fusion, their energy is released only through the gradual radiative cooling of their interiors. Sirius B will thus steadily cool and fade over time. The evolutionary history of Sirius B gives astronomers valuable insights into the fate of stars like the Sun, which will eventually go through a similar process and become white dwarfs after exhausting their nuclear fuel. Sirius B is classified as a Da2 white dwarf. The D indicates that it is a degenerate star, meaning it no longer undergoes fusion and is in the final phase of stellar evolution. The A refers to its hydrogen-dominated atmosphere, which is common among white dwarfs. The 2 inches indicates its surface temperature, which is around 25,000 K. Sirius A has an unusually high metallicity compared to other stars of similar type. Its metallicity is measured to be about Ph = plus 0.5, meaning it has around 3 times the iron content relative to hydrogen compared to the Sun. This is significant, as higher metallicity in stars can influence various factors such as stellar opacity, evolution, and the formation of planets around them. The enhanced metallicity of Sirius A might be explained by its companion, Sirius B. When Sirius B evolved into a red giant before shedding its outer layers and becoming a white dwarf, it likely transferred some of its material, enriched with heavier elements, to Sirius A. This process, known as mass transfer, could have increased the metallicity of Sirius A, explaining the unusually high levels of metals observed in its atmosphere. Another contributing factor could be that Sirius A is a part of a younger stellar population, which generally contains higher concentrations of metals because it formed from material that had already been enriched by previous generations of stars. As an A-type star, Sirius A exhibits a spectrum dominated by strong hydrogen absorption lines, which are the most prominent features in the spectra of stars of this type. A-type stars have surface temperatures between 7,500 and 10,000 K, and at these temperatures, hydrogen atoms are in an excited state that strongly absorbs light at specific wavelengths, particularly in the Balmer series. These absorption lines appear as dark bands in the star's spectrum. In the case of Sirius A, the hydrogen absorption lines are particularly prominent. In addition to hydrogen lines, the spectrum of Sirius A also contains metallic absorption lines, which are the signatures of elements heavier than helium, such as iron, Fe, calcium, Ca, zinc, Zn, and strontium, Sr. These lines are less prominent in stars with normal chemical compositions, but are more pronounced in chemically peculiar stars like AM stars. The presence of these enhanced metal lines in Sirius A's spectrum indicates that it is a chemically peculiar star of the AM type. AM stars, metallic line stars, are a subclass of A-type stars that show enhanced metal lines in their spectra. The AM designation stands for A-type star with metallic lines. This peculiar chemical makeup is thought to result from elemental diffusion, a process where certain elements sink or rise within the star's atmosphere due to the effects of gravity and radiation pressure. The abundance of metals in the star's outer layers does not necessarily reflect the star's overall composition, but rather results from processes occurring in its atmosphere. The peculiar chemical abundance patterns seen in AM stars suggest that their atmospheres have undergone some degree of separation of elements, rather than mixing uniformly throughout the star. In AM stars like Sirius A, heavier elements like iron and zinc are levitated to the surface by radiation pressure, while lighter elements like helium sink deeper into the star's interior. The metallicity of Sirius B is not as straightforward to measure as it is for Sirius A. As a white dwarf, Sirius B no longer undergoes fusion reactions and has a very high surface gravity, causing gravitational settling. This means that the heavier elements in Sirius B's atmosphere sink toward the core, leaving the outer layers almost entirely composed of hydrogen. As a result, the observed spectrum of Sirius B shows very little in the way of metallic lines, and its outer layers appear to be nearly metal-free. However, This does not mean that Sirius B lacks metals entirely. In fact, during its earlier stages as a B-type main sequence star, it would have contained significant amounts of heavier elements, similar to other stars of its type. These metals are likely now concentrated deeper within the white dwarf, beneath the outer layers of hydrogen. Sirius B is believed to be primarily composed of carbon and oxygen, which are the remnants of the nuclear fusion processes that took place when it was a main sequence and later a red giant star. During its life as a B-type star, Sirius B fused hydrogen into helium in its core, like all main sequence stars. As it evolved into a red giant, the core temperatures increased, allowing the helium to fuse into carbon and oxygen via the triple alpha process. This process creates carbon nuclei, and with further fusion reactions, some of the carbon can combine with helium to form oxygen. Once the star could no longer sustain nuclear fusion, it shed its outer layers and collapsed into a white dwarf. The result is a dense core primarily composed of carbon and oxygen. These elements are thus the byproducts of the nuclear reactions that occurred during the star's earlier evolutionary phases. The distance to Sirius has been a subject of estimation for centuries, with modern methods providing precise measurements. In ancient times, astronomers could not accurately measure stellar distances, so early estimates were speculative. Cultures like the Egyptians and Greeks focused more on Sirius's position in the sky for calendar and seasonal purposes, rather than its distance from Earth. It wasn't until the 17th century that Christian Huygens made one of the first attempts to estimate the distance. In his 1698 book, Cosmotheros, Huygens assumed that Sirius had a similar intrinsic brightness to the Sun. By comparing its apparent brightness to that of the Sun, he estimated Sirius to be about 27,664 times the Earth-Sun distance, or roughly 0.437 light-years away, which significantly underestimated the true distance. This miscalculation arose because Sirius is far more luminous than the Sun, a fact unknown at the time. In the 18th and early 19th centuries, astronomers attempted to use parallax, the apparent shift in a star's position due to Earth's orbit around the Sun, to measure Sirius's distance. Early attempts by figures like Jacques Cassini suggested a parallax of around 6 arcseconds, but these measurements were far from accurate due to limitations in observational technology. A more refined estimate emerged from Scottish astronomer Thomas Henderson's observations in the 1830s. Using data collected from South Africa, Henderson estimated a parallax of 0.23 arcseconds, which translated to a distance of roughly 14 light-years, closer to the correct value, but still an overestimate. Throughout the 19th century, astronomers gradually improved their methods, with estimates converging on a parallax of about 0.25 arcseconds, though this still overestimated the actual distance. Modern precision came with the launch of the Hipparcos satellite in 1989 by the European Space Agency. Hipparcos provided highly accurate parallax measurements for nearby stars, including Sirius, determining its distance to be about 8.6 light-years, with a parallax of 0.379 arcseconds. This marked a significant leap in accuracy compared to earlier ground-based measurements. More recently, the Gaia Space Observatory, launched in 2013, has further refined these measurements. Gaia's data, specifically from Data Release 3, has confirmed the distance to Sirius to be around 8.6 light-years. The Sirius binary system is characterized by a highly elliptical orbit with a period of approximately 50.1 years. The separation between the two stars varies from 8.2 AU at its closest, periastron, to 31.5 AU at its farthest, apoastron. The semi-major axis of the orbit is about 20 AU, which is roughly the distance between the Sun and Uranus. The semi-major axis is the radius of the most elongated part of the ellipse, in contrast to the shorter semi-minor axis. The orbital plane of the Sirius binary star system is tilted at an angle of approximately 44.6 degrees relative to the plane of the solar system, also known as the ecliptic plane. Given the position in the sky of Sirius, this means that if you were observing the Sirius system from Earth, you would see the orbit of Sirius B around Sirius A at an inclination that is neither edge-on nor completely face-on, but moderately tilted. The orbital motion of Sirius has been extensively studied, providing valuable data for testing theories of stellar dynamics and the physics of binary star systems. By studying the orbit of Sirius B and interactions with Sirius A, astronomers can gain insights into the later stages of stellar evolution, particularly the processes involved in mass loss, the formation of white dwarfs, and how binary systems evolve over time. Moreover, the precise observations of the Sirius binary system, particularly its orbital period and separation, ranging from 8.2 to 31.5 AU, provide critical data for refining models of binary star formation and interaction. This data also helps improve understanding of how orbital energy and angular momentum are exchanged between stars in binary systems. The Sirius system has also been important for testing Einstein's theory of general relativity. One key prediction of general relativity is that light will experience a gravitational redshift as it escapes the intense gravitational field of a massive object, such as a white dwarf. Sirius B, being a white dwarf with an extremely dense mass, provides an ideal environment to observe this effect. In 1925, astronomers observed the gravitational redshift of light from Sirius B, confirming Einstein's prediction. The light emitted from Sirius B is shifted to longer, redder wavelengths as it climbs out of the star's strong gravitational well. This phenomenon is one of the earliest successful confirmations of general relativity outside the solar system and has provided further evidence for the theory's accuracy. The orbital motion of the Sirius binary system causes the two stars to vary in angular separation, ranging from a minimum of 3 arcseconds to a maximum of 11 arcseconds. When the stars are at their closest approach, distinguishing the white dwarf from its brighter companion is difficult and requires a telescope with at least a 300 mm 12-in aperture and optimal seeing conditions. After reaching periastron in 1994, the stars began moving apart, making it easier to separate them through a telescope. Apoastron occurred in 2019, but the greatest angular separation, 11,333 arcseconds, was observed from Earth in 2023. Both Sirius and the Sun belong to distinct stellar populations in the Milky Way, yet neither is currently part of a tightly bound star cluster. However, both have been associated with larger stellar groupings and moving groups that provide insights into their formation and shared motion through space. For many years, astronomers believed that Sirius might be a member of the Ursa Major moving group. The Ursa Major moving group is a loose association of stars that share a common motion through space, having formed from the same stellar nursery approximately 500 million years ago. The members of this group include several bright stars from the Ursa Major constellation, and the stars have similar ages, compositions, and trajectories. However, more recent research has cast doubt on Sirius's membership in this group. Sirius, with an estimated age of only 200 to 300 million years, is much younger than the typical stars in the Ursa Major moving group. Additionally, its higher metallicity suggests that it formed in a different environment. As a result, while Sirius shares some motion characteristics with stars in the Ursa Major moving group, it is now generally believed that Sirius is not a genuine member of this group. Sirius may instead be associated with the Sirius supercluster, a grouping of stars that share similar motion through space. This supercluster includes stars such as Beta Aurigae, Alpha Coronii Borealis, and Beta Eridani, which, like Sirius, appear to have formed from a similar region of the galaxy and share common motion characteristics, though they are widely dispersed. The Sun is not part of a tightly bound star cluster either, but it is often linked to a stellar association known as the Local Association, or the Pleiades moving group. This group consists of stars that share a similar velocity through space and are thought to have formed from the same molecular cloud around 100 to 300 million years ago. The Local Association includes stars from the Pleiades cluster, Hyades, and other prominent stars in nearby constellations. While the Sun shares many of the same characteristics, such as metallicity and trajectory, suggesting that it may have been born in a similar region of the galaxy as the other stars in the local association. The Sun itself is much older, 4.6 billion years old. Its motion is somewhat different from other stars in this group. The Sun itself is not a coeval member, meaning it did not form at the same time or from the same molecular cloud as these younger stars. Today, both Sirius and the Sun are relatively isolated in space and are not members of any open clusters or globular clusters. They are moving through the galaxy as part of the broader stellar population in the Milky Way's disk. While both stars may have been born in clusters or associations that have since dispersed, they no longer reside in tightly gravitationally bound groups of stars. Their current isolation reflects the common fate of many stars in the galaxy, which are born in clusters but eventually drift apart as they orbit the galactic center. So, are there any planets in the Sirius system? Currently, there is no confirmed evidence of planets in the Sirius system, though there has been speculation and searches for possible planetary companions. Given the proximity and brightness of the Sirius A and B stars, the system has long been of interest to astronomers in the search for exoplanets. Astronomers have conducted multiple searches for planets around Sirius A and Sirius B, particularly in recent years with advanced techniques like direct imaging and radial velocity measurements. Infrared observations from the IRAS space telescope revealed some excess infrared radiation from Sirius A, which raised the possibility of dust or planetary material, but follow-up studies have not confirmed the presence of any planets. A 2015 study using the Very Large Telescope, VLT, ruled out the presence of any massive Jupiter-sized planets orbiting within a few astronomical units of Sirius A, down to a distance of about 10 AU. They found no planets larger than about 4 Jupiter masses. One of the main obstacles to planets in the Sirius system is the binary nature of Sirius A and B. The two stars are in a close elliptical orbit, with distances ranging from 8.2 to 31.5 AU. This creates a gravitational environment that would make it difficult for planets to form or maintain stable orbits, especially near the stars. Additionally, Sirius A's extreme brightness makes detecting faint planetary signals difficult, as the star's light often overwhelms potential planetary signatures. Furthermore, Sirius B, now a white dwarf, went through a red giant phase earlier in its life. This phase likely destroyed or engulfed any planets that might have formed around it, and the resulting mass loss may have further destabilized planetary orbits around Sirius A. While no planets have been confirmed, there remains a possibility that planets could exist at greater distances from the binary system, beyond the strong gravitational influence of Sirius A and B. Such planets, if they exist, would likely have wide orbits, making them difficult to detect with current technology. Smaller Earth-sized planets, too, could exist, but they would present an even greater challenge for detection due to their faint signals. But let us look closer at the possibility of detecting an Earth-like planet in the Sirius system and ask ourselves, is it a paradox, as in the Fermi paradox, that we have not detected alien life forms? Or is it completely natural, given we cannot even reliably see Earth-sized planets around the very closest stars? While modern astronomical technology has made remarkable advances, we still face significant challenges in detecting Earth-like planets around stars like Sirius. Our current technology is not yet capable of easily identifying such planets unless certain favorable conditions are met. One of the key methods used for detecting exoplanets is the transit method, where planets are identified by the slight dimming of a star's light as a planet passes in front of it, or transits, from our point of view. However, this method only works if the orbital plane of the planet is aligned such that it passes directly between its star and Earth. The chances of such a favorable alignment are low, as the system's orbital inclination would have to be perfectly oriented for transits to be observed from Earth. In most cases, even if an Earth-like planet exists in the system, we wouldn't detect it through transits unless we were observing the system from just the right angle. Additionally, Sirius A is the brightest star in the night sky, which presents its own challenges. The intense brightness of Sirius A makes it extremely difficult to pick up the faint signals that a small Earth-sized planet would produce, especially if it is orbiting far from its host star. Techniques like the radial velocity method, which detects the wobble of a star due to the gravitational pull of an orbiting planet, are also limited when it comes to small planets around very bright stars. The extreme luminosity of Sirius A tends to overwhelm the subtle signals caused by a planet's gravitational influence, making it hard to differentiate planetary effects from other stellar activity or noise. In the case of direct imaging, while we have made strides in capturing images of large gas giants around distant stars, detecting an Earth-sized planet around Sirius would require even more advanced technology than we currently have. The brightness of Sirius A and the close proximity of Sirius B as a white dwarf create a challenging environment for capturing clear images of any potential planets. Furthermore, Sirius B, having gone through a red giant phase in its past, may have disrupted the orbits of any planets that could have formed in the system, further complicating the search for Earth-like planets. Any planets that may have survived or formed afterward would likely be at wide distances, making them harder to detect with existing techniques. In an article in the Astronomical Journal titled An Imaging Search for Post-Main Sequence Planets of Sirius B by Lucas et al. Of 2021, astronomers used deep imaging to investigate the presence of planets around Sirius B. The goal was to explore how planets might survive or form after their host star has evolved beyond the main sequence. The researchers used high-contrast imaging with the Keck NIRS-C2 telescope across 3 observational periods in 2020, focusing on detecting planets within a certain range of Sirius B, primarily from sub-Jupiter-sized planets down to as small as 0.7 Jupiter masses. They achieved detection limits that could rule out large planets at separations within 1 AU. The fate of a planet orbiting a star that has evolved beyond the main sequence is uncertain and violent. As a star enters its giant branch phase, it expands dramatically, and any nearby planets must avoid being engulfed or torn apart by tidal forces. Surviving planets are subjected to intense stellar winds and high luminosity, which enrich the circumstellar environment with metals and dust. These winds and radiation can heat and destabilize the planet's orbits, sometimes ejecting them entirely. Numerical models suggest that for a planet to escape such effects, it must orbit at least 5 AU away from its host star. When combined with the phenomenon of adiabatic orbit expansion, planets closer than 10 AU are unlikely to survive. Due to Sirius B's evolutionary history, including its previous expansion as a giant star, it is unlikely that any first-generation planets survived. The most stable orbit for a companion around Sirius B is estimated to be about 1.5 AU. The article notes that the study of planetary systems around evolved stars, particularly post-main sequence, post-MS stars, is still an emerging field with limited knowledge. In their search for planets around Sirius B, the researchers conducted high-contrast imaging but found no consistent evidence of substellar companions. Several signals appeared in the data, suggesting possible planetary candidates, but further analysis ruled them out as non-Keplerian objects, likely artifacts of scattered starlight or residual noise. These findings were consistent across multiple epochs, leading to the conclusion that no planets exist around Sirius B within the detection limits of the study. Let us now have a closer look at the significance of Sirius historically around the world. Sirius has been known and observed since ancient times, playing a crucial role in various cultures. The Dogon people of Mali, West Africa, have a fascinating and complex mythology surrounding Sirius, which has captured widespread interest due to their seemingly advanced astronomical knowledge. According to their oral traditions, the Dogon possessed detailed information about Sirius long before modern science confirmed certain aspects of the star system. This has led to speculation about the origins of their knowledge. In Dogon cosmology, Sirius is known as Siggi-Tolo, star of the Sigwi, and they speak of a companion star called Po-Tolo, star of the Seed, which is described as incredibly small, dense, and invisible to the naked eye. Remarkably, This aligns with what modern science has discovered about Sirius B, the white dwarf companion to Sirius A, which is also invisible without the aid of telescopes. The Dogon describe Potolo as the smallest and heaviest of stars, closely matching the scientific understanding of white dwarfs. Even more astonishing is that the Dogon claim Potolo orbits Sigitolo in a 50-year cycle, which mirrors the 50.1-year orbital period of Sirius B around Sirius A. This level of precision in their oral tradition has intrigued many, especially given that this information was reportedly known to the Dogon long before it was discovered by Western astronomers in the 19th and 20th centuries. Central to the Dogon's mythology are the Namo, amphibious, semi-divine beings who are said to have come from the Sirius system. According to their creation story, the Namo descended from the sky in an ark and brought knowledge, including astronomical wisdom, to the Dogon people. The Namo are not only central to the Dogon's creation myth, but also play a significant role in their religious ceremonies, agriculture, and social organization. The Dogon believed that the knowledge of Sirius and its companion stars was passed down by these beings through generations, particularly during the Sigui ceremony, a major religious event held every 60 years to honor the cycle of Sirius. The Dogon's precise knowledge of the Sirius star system, especially details about Sirius B, has sparked debate and controversy. Some researchers, such as Robert Temple in his book The Sirius Mystery, 1976, have suggested that the Dogon's understanding of Sirius B may point to ancient contact with extraterrestrial beings or a lost advanced civilization. Others, including anthropologists and astronomers, argue that the Dogon could have obtained this knowledge from modern Western sources during the early 20th century or through cultural diffusion. However, the Dogon people themselves attribute their knowledge to their ancient traditions and the teachings of the Namo. The case of the Dogon and Sirius remains a compelling mystery, blending mythology, cosmology, and astronomy. While scientific explanations have been proposed, the Dogon's connection to Sirius reflects their deep cultural and spiritual relationship with the stars and the universe. Whether derived from ancient teachings or outside contact, the mythology surrounding Sirius holds an important place in Dogon spirituality, symbolizing their cosmic connection and reverence for the heavens. The Serer people of Senegal, Gambia, and Mauritania have their own rich traditions and cosmology, in which Sirius holds significant importance. In Serer mythology, the star Sirius, known as Unir, is deeply connected to their spiritual beliefs and agricultural practices. It is seen as the star of creation and is associated with fertility, life cycles, and the cosmos itself. The Serer people regard Unir as a symbol of life and regeneration, and it plays a crucial role in their farming calendar. The appearance of Sirius in the sky marks the beginning of the rainy season, which is vital for their crops. This is similar to the way other ancient cultures, like the Egyptians, associated Sirius with the flooding of the Nile. For the Serer, the rising of Unir signals a time of renewal and abundance, and its celestial influence is celebrated in rituals related to planting and harvesting. Unir is also a central figure in Serer cosmology, where it is believed to be linked to the creation of the universe. The Serer creation myth speaks of the primordial star and its connection to Rog, the supreme deity in Serer religion. The star is seen as a pathway or bridge between the earthly and the divine realms, symbolizing the connection between humans and the spiritual forces governing life and the cosmos. In Serer culture, the star Unir is often depicted as a five-pointed star, which represents both the star itself and the human being, with the 5 points symbolizing the head, arms, and legs. This symbol is used in art, clothing, and sacred objects, reflecting the deep reverence the Serer people have for Unir as a guiding force in their spiritual and daily lives. The Serer people's relationship with Sirius reflects a broader pattern of star veneration found in many ancient cultures. For the Serer, Unir is not just a celestial object, but a powerful symbol of creation, fertility, and the cyclical nature of life, playing a vital role in their cosmology, spirituality, and agricultural practices. As mentioned previously, the Greeks closely observed the heliacal rising of Sirius, which occurs when the star first becomes visible at dawn after a period of being hidden by the sun. This event marked the onset of the hottest days of summer, a period the Greeks called the dog days. The appearance of Sirius at dawn was thought to bring intense heat, drought, and even sickness. In Greek literature, the star was often described as burning or scorching due to its brilliance and the uncomfortable heat that followed its rise. The Greeks believed that Sirius's rising influenced both humans and animals. People feared that its intense brightness caused plants to wither, men to become weak, and animals, especially dogs, to behave erratically. This connection between the star and adverse effects on health gave rise to the phrase dog days, which still refers to the hottest time of the year. In Greek mythology, Sirius was linked to the hunter Orion and his faithful dog, represented by Canis Major in the sky. The myth explains that both Orion and his dog were placed among the stars after their deaths, and Sirius, as part of the Canis Major constellation, follows Orion across the heavens. In Roman culture, Sirius was also associated with heat and the dog days of summer, much like in ancient Greece. The Romans referred to the star as Canicula, meaning little dog, but still linking it to the constellation Canis Major, just as the Greeks did. The period when Sirius rose in conjunction with the sun, around late July, was known as the Dies Canicularis, the dog days. This stretch of time was believed to bring oppressive heat, lethargy, and discomfort. The Romans, like the Greeks, believed that Sirius had a direct impact on health and the environment. The star's rising was thought to cause droughts, crop failures, and sickness. It was even associated with wheat rust, a blight on crops. To ward off such misfortune, the Romans held a festival around the time of Sirius's heliacal setting, which occurred in late April. They would sacrifice a dog, along with offerings of wine and incense, to the goddess Robigo, who was thought to protect crops from rust and other diseases. This festival, called the Robigalia, was a way of ensuring that Sirius's harmful influence would be mitigated, particularly in relation to the harvest. In Roman literature, Sirius was sometimes depicted as a symbol of fiery intensity. The poet Virgil in his Georgics described Sirius as bringing fever to the earth when it rises, reflecting the widespread belief that the star's brilliance could scorch the land and its inhabitants. Sirius, in Roman thought, was thus a harbinger of both physical and agricultural challenges, symbolizing the fierce heat and hardships of summer. Its importance in Roman culture was reflected in both religious practices and literary references, showing how deeply the star influenced their understanding of seasonal cycles and natural events. To the ancient Egyptians, Sirius also held immense significance, both astronomically and religiously. Known to them as Sopdet, Sirius was associated with the goddess Sopdet, who was linked to fertility and the annual flooding of the Nile River, a vital event for Egyptian agriculture. The heliacal rising of Sirius coincided with the onset of the Nile's annual flooding. This event, which occurred around mid-July in ancient times, was crucial for the Egyptians, as the floodwaters would deposit fertile silt along the riverbanks, making the land suitable for growing crops. The regularity and predictability of Sirius's rising made it an essential astronomical marker for the Egyptian calendar, effectively signaling the start of the new year. The Egyptians revered Sirius as the bringer of life and renewal due to its association with the life-giving floods. The goddess Sopdet, often depicted with a star on her head, represented the regenerative powers of the Nile's waters. This connection between the star, the river, and the goddess was deeply embedded in the religious and agricultural cycles of ancient Egypt. Additionally, Sirius was a key marker in Egyptian astronomy. as its precise reappearance in the sky offered a reliable way to synchronize their calendar with the solar year. It was so important that the Egyptian civil calendar was sometimes referred to as the Sothic cycle, based on the star's 460-year cycle of heliacal risings relative to the calendar year. Overall, Sirius played a central role in Egyptian life, symbolizing the forces of nature, renewal, and divine order. It was not just an astronomical body, but a symbol of hope and sustenance, tied to the prosperity of the land and the well-being of the people. In ancient Persian culture, Sirius was known as Tishtria, and it played a vital role in their cosmology and religious beliefs, particularly within Zoroastrianism, the dominant religion of ancient Persia. Tishtria was revered as a powerful deity associated with rainfall, fertility, and the battle against drought. In Zoroastrian mythology, Tishtria was depicted as a radiant white horse, symbolizing purity and strength. This celestial figure was believed to engage in a cosmic struggle with Apayosha, the demon of drought. The battle between Tishtria and Apayosha was critical for ensuring that rain would fall and bring life to the crops and lands. According to the mythology, when Tishtria won this battle, rain would come to the earth, thus ensuring the fertility of the land and the prosperity of the people. The star Sirius, as Tishtria, was associated with the monsoon rains that were crucial to agricultural success. Its appearance in the sky was seen as a sign of the forthcoming rains, much like its role in other ancient cultures where it was connected to important natural events. The importance of Tishtria extended beyond mere meteorological phenomena. It symbolized the struggle between good and evil forces, reflecting broader Zoroastrian themes of cosmic duality. As a divine warrior, Tishtria's victory over drought was part of the Zoroastrian concept of maintaining Asha, order and truth, over Druj, chaos and falsehood. In Persian astronomy, Tishtria was also associated with the summer solstice, marking an important point in the annual agricultural and spiritual cycle. The star's bright, shining appearance made it a prominent figure in the night sky, and its role in bringing the life-giving rains made it central to both religious practices and practical concerns of the ancient Persians. Thus, in ancient Persian culture, Sirius as Tishtria was not only an important celestial body, but also a symbol of hope, fertility, and the ongoing battle between the forces of life and destruction. In ancient Chinese culture, Sirius was known as the celestial wolf, Tianlang Tianlang. This name reflects its association with wolves, a creature that symbolized power, aggression, and sometimes malevolence. Sirius, with its brilliant light, was perceived as a menacing presence in the sky, fitting the wolf's role as a hunter and predator in Chinese mythology. The star was part of the constellation of Jingsu, which was one of the 28 lunar mansions, or shu, used in Chinese astronomy. The lunar mansions were a system of constellations that functioned similarly to the zodiac in the West, but they tracked the moon's progress across the sky rather than the sun's. Jing represented a well, and Sirius, within this mansion, symbolized both the wolf and a vigilant guardian. The celestial wolf connection also linked Sirius to military themes. In times of war, the star was sometimes seen as an omen of conflict and violence, its bright appearance reflecting the aggressive and predatory nature of warfare. The Chinese saw celestial phenomena as having direct influence on earthly events, so a bright, prominent star like Sirius was considered to have significant power. Additionally, Sirius was used for agricultural timing, as it was in many ancient cultures. Its visibility in the night sky helped the Chinese track seasonal changes, which were crucial for determining planting and harvesting times. The appearance of Sirius signaled the onset of winter, aligning it with a period of scarcity and challenges, further reinforcing the star's association with wolves and survival during tough times. Thus, in ancient Chinese culture, Sirius was a multifaceted symbol, a powerful celestial wolf with connections to war, winter, and the survival of both people and nations. The indigenous peoples of North America held a variety of beliefs and associations with Sirius, reflecting its prominence in the night sky. Different tribes had distinct names and stories connected to the star, often linking it to animals, spirituality, and the afterlife. The Inuit people along the Bering Strait, today Alaska, referred to Sirius as the moon dog. This name reflects the star's bright, consistent presence in the sky, like a companion to the moon. It was seen as a guardian star and held a protective role, much like a dog's watchfulness. The Pawnee people of the Central Plains, today Nebraska, recognized Sirius as the wolf star. The wolf was considered a significant spiritual animal for the Skiddy Pawnee, and Sirius was believed to be a guiding star for wolves. In their cosmology, Sirius played an important role in hunting and the spirit world, symbolizing strength and survival. The Skiddy Pawnee divided the sky into star gods, and Sirius was part of the larger celestial scheme that influenced their daily lives, rituals, and seasons. For the Cherokee, today southeastern United States, Sirius was connected with the path of souls, an important spiritual journey that a person's soul would take after death. Sirius, along with Antares, was believed to guard either end of this celestial path, helping guide souls to the afterlife. This association with the afterlife gave the star deep spiritual significance. Among the Seri and Tohono O'odham, today Arizona and northern Mexico, Sirius was often associated with a dog. The star was thought to follow Pleiades, or seven sisters, in the night sky, as a dog might follow a hunter or a pack of mountain sheep. The association with dogs reflects the star's loyalty and connection to the cycle of nature and hunting. These associations across North American indigenous cultures show Sirius as a star of great significance, often symbolizing protection, guidance, and connections to animals, especially dogs and wolves, as well as the afterlife and spiritual journeys. For the Polynesians, Sirius, known as Taurua or A, held great significance in their navigation, mythology, and cosmology. As a seafaring people, the Polynesians used stars extensively to navigate across the vast expanses of the Pacific Ocean, and Sirius, being the brightest star in the night sky, was one of their primary celestial guides. In Polynesian navigation, AA was particularly important because of its brightness and its position in the sky. It helped Polynesian wayfinders to orient themselves during long ocean voyages, especially when traveling between islands. The star's appearance would signal specific times of the year, aiding in planning voyages and activities. The precision of Polynesian navigation is legendary, and stars like Sirius played a key role in their ability to explore and settle islands spread over thousands of miles. Sirius also featured in Polynesian mythology and cultural stories. In some traditions, Sirius was associated with gods and ancestors, embodying spiritual power and guidance. Its rising and setting were interpreted as celestial events of importance, often connected with the changing seasons, agricultural cycles, and fishing practices. In Maori culture of Aotearoa, today New Zealand, Sirius is referred to as Takurua. It is linked with winter and the colder months, and its appearance marked important seasonal transitions. For some Polynesian groups, the star was connected to the goddess of winter, or it represented a celestial being that influenced weather patterns, tides, and harvests. Sirius also played a role in social and religious ceremonies. Its visibility at certain times of the year was sometimes seen as an auspicious sign, guiding rituals or marking important festivals in the Polynesian calendar. This celestial connection reinforced the spiritual and practical importance of Sirius within Polynesian culture. Today, Sirius is still a reference often seen in modern culture, in literature, names, etc. One example is that Sirius is one of the 27 stars on the Brazilian flag. And here are 10 examples of things named Sirius, other than the star system. 1. Sirius Satellite Radio, a popular satellite radio service in the United States, now part of Sirius XM. 2. Sirius Black, a fictional character in the Harry Potter series by J.K. Rowling. 3. Sirius XM Holdings Inc., an American broadcasting company providing satellite and online radio services. 4. Sirius Ship, the first steamship to cross the Atlantic Ocean in 1838. 5. IK Sirius, a Swedish sports club based in Uppsala. 6. Sirius, dog food brand, a brand of dog food sold in Russia and Eastern Europe. 7. Sirius Software, a video game company active in the early 1980s, known for producing games for the Apple II computer. 8. Sirius Minerals, a UK-based company focused on mining and fertilizer production. 9. Sirius Academy, a secondary school located in Hull, England. 10. Sirius Rocket, a research rocket developed in Germany for high-altitude experiments. As Sirius continues its journey through space, it will undergo several changes over the coming millennia. The star is currently moving closer to the solar system and will reach its peak brightness in about 60,000 years. Around the same time, due to the precession of the Earth's axis, Sirius will become the southern pole star, being within 1.6 degrees of the south celestial pole in the year 66270. This is due to axial precession and proper motion of Sirius itself, which moves slowly in the south-southwest direction, so it will be visible from the southern hemisphere only. Eventually, Sirius will begin to move away from the solar system, gradually becoming fainter over time. However, it will continue to be the brightest star in the night sky for approximately 210,000 years, at which point Vega will surpass it in brightness. In the distant future, Sirius A will exhaust its nuclear fuel and evolve into a red giant. After shedding its outer layers, it will collapse into a white dwarf, much like its companion, Sirius B. The two white dwarfs will then continue to orbit each other, slowly cooling and fading over billions of years. Sirius, the brightest star in the night sky, has fascinated humanity for millennia. Its brilliance is not only a result of its intrinsic luminosity, but also its proximity to Earth, making it a focal point for both ancient and modern astronomy. From its role in ancient cultures and mythologies to its contribution to the development of astrophysics, Sirius has left an indelible mark on human history. If you are still awake and want more content, go ahead and check out our other episodes. And if you want to help create even more, please consider supporting us. While this manuscript was written by AI and read by me, an AI voice, creating this content still required production time from a human being. If you want to support the production, please make a donation to the Milky Way Traveler over at Patreon. To do so, follow the link in the show notes or search for the Milky Way Traveler at Patreon. If anything is incorrect in this episode, if you are missing some information, or if you just want to add your view, feel free to make a comment in the comment section for this episode. Now thank you for joining this trip, and have a beautiful and wonderful night, with sweet dreams once you get there.